Welcome to episode 10. No, you haven't missed episode 9. I decided to skip episode 9 because I was preparing it and I fell behind. I made a lot of new progress and I decided, screw it, work on part 10 and I'll include the content of what was going to be part 9. So yeah, without further delay, because there's much to get through, let's get into it. So I'm going to explain this TCP sockets method I implemented, which I use to transfer in-game variable data to the Python environment from the emulator to Python, and as well the screen capture. I implemented a method of returning a single screen frame. I've implemented what is a real-time version of Gym, or a library for implementing a real-time Gym environment. I show you a random agent working. I will show you some additional variables that were discovered that may be useful for this activity, and the initial results of a totally unoptimized default PPO agent I implemented with very limited training. I also experimented with A3C, but yeah, I need to look into that more. I want to say special thanks to a bunch of people, and probably it's not an entire list. So the first off is Jan, who is one of the developers for the Trackmania reinforcement learning project and the author of RT Gym, Real-Time Gym. He's been extremely patient with helping me understand his own documentation, which, to be honest, for an open source project on GitHub, it's really one of the ones that's been most well documented, including the tutorials. So whenever Jan releases an update, I almost never find documentation that is out of sync with the update he implemented. That's amazing. I want to thank the person who I know as Sevs, who also has a YouTube channel. I'll put a link in the description. So basically, Sevs reached out to me when he saw one of the earlier videos because he wanted to do something similar to use reinforcement learning in another PlayStation 1 game, Mega Man X. So in the end, he actually went a different way from me in the sense that he used a different emulator and different reinforcement learning framework. But he's been a great support. So he's finished this project. So he knows what he's doing. And that was encouraging to me. But also I was able to bounce off ideas against him and get some advice from him. I also came across someone I know as Jamie T, who also came across my videos and reached out to me to get in contact because he was also reverse engineering Gran Turismo. He's way better at it than I am, and we compared notes, and he has found some variables that I had not. I see also that he found some from me. So for example, boost, the boost variable, he was not as confident as I am, but he made a memo, a comment in his deconstruction or decompilation and the R008 video, so respect to that for also keeping a record of from whom, where he found it. Not that it matters, but I think this is what makes the community respectable. I have to thank Nicholas, who's been supporting me with the networking type of issues for the TCP sockets. He also has been updating and adding features to Redux, I'd say partially in support of this project. So one of the things he added is protobuf, which I'll speak about later. Alerus is someone I met recently on a reinforcement learning forum who knows a fair bit about reinforcement learning in racing games such as Gran Turismo. And yeah, he encouraged me to proceed this project, and he acknowledged from a very, very relevant experience how tricky it is, or maybe to make something that's not developed for machine learning to be used in machine learning. And finally, Daniel S., who supported me so much with understanding the reinforcement learning framework I decided to use, which I'll explain at the end. So, screen transfers. We previously looked at different methods of capturing screens from the game, from the emulator, and I later decided to switch to protobuf. So protobuf is a library or an API, or both, developed by Google for serializing and compressing data to transfer over networks. And that's what we are using to transfer from Redux via Lua to the Python environment. And so I did some tests to check, besides sending, for example, vehicle speed as an integer, what's the speed of it transferring the screen capture directly from the emulator to Python. Amazing. It's far better than the other methods because it's able to be as fast as the emulator if necessary. So for a PAL game, here let's take the 500 frames dumped from the emulator to Python. If I don't try to redisplay it in Python, for 49.99 frames per second in the emulator, in Python we can maintain 49.9, so practically the same. I did the same test on NTSC because NTSC games run at 60 frames per second, or according to Redux 59.99. And again, in Python, we could maintain 59.9. It's slower when I make Python draw these images, and I'm using, I think I'm using Pillow, which is not the best for high refresh rates. But at least it's still 52.7, so you can see this frame rate is almost as high as we could peak with the other methods. Then the issue which occurred was what I'm calling the FIFO effect, which is when the Python environment is occupied and the emulator is sending images. When the Python environment is ready to work again, it will consume all the images it has not yet processed. So here what I did is, this is the emulator output, and here is the Python environment. And I'll move this window, which will cause the Python loop to pause or stall until this window is positioned again. And then you'll see it processing the images it had not yet seen very rapidly. So yeah, it will look like a fast forward movie till the video synchronizes again. So if you imagine these two cars are moving, and then one of them, this is the Python side, and then it needs to speed up to catch up again. So have a look. So these two videos are in sync for now. Now we've frozen the Python. Now we'll resume, and you see it's like fast forwarded movie until it's in sync. I'll do it again. And again, fast forward. So this would be an issue, because if the Python environment, for example, needs to evaluate what action to take, and this might take some time, and if for some reason there's a stall on the Python side, it will first of all decide the action for a frame that is too old. But what's even worse, the next action it will try to evaluate will be for a frame that is also very old, and it will keep trying to do this. And if the delay is systematic, so if the Python environment is always going to be a little bit late, it's going to get progressively more and more behind from real time. So this method was not what we need. So this is the gist of the method I've come up with, and this is again where Nicolas' brainstorming and support helps. So basically, to receive a frame, and this is the example for receiving a single frame. So the Python sends a pong, ping pong, ping signal. So one tells it, I'm ready to receive. And this is only it's not mandatory, but it's there so that the emulator can also skip preparing frames if Python is not ready to receive them. Maybe it's unnecessary, but I think it can help keep the workload of the computer lower, which I think is going to be necessary since reinforcement learning, especially training, can be resource intensive. So I don't want to waste resource ahead of time. But then what's going to do is going to do this loop for as long as it can, and it will exit when it doesn't have to. So what it will do after sending this pong, to the emulator, it will try to receive data. And when it's done receiving data, it's going to check, hey, was an exception triggered? And this exception which might have been raised, is hopefully the exception for when it cannot receive any data, because the Redux, the emulator, has nothing to send. So we're in between frames. Then the Python side is going to keep storing all the data it receives, and based on the header contents of these packets it's receiving, or stream it's receiving, evaluate, does it have enough bits and bytes of data to make up the whole frame, so the image and the variable data. If it does, that flag will be set to true. So we have an exception, which means we've captured or received or consumed all the data that there is to consume. And we know that at least we had one entire frame, which is probably or definitely the latest frame that there is. And then we can process that, decode the image, convert it from the Redux method of data into the format which we need in Python. And here for debugging, I have this part, which is what's actually drawing the emulator rendering screen in Python. So when that's true, when this has succeeded, it will trigger this return, and we're done with the loop. So, and here is it in action. So again, I'm going to move that window, and you can see it's synchronized. Move the window again, and it's synchronized. And I've also tested the opposite. Pause the emulator and then resume and see what happens. Whatever we do, here it is. I pause the emulator. I can move this window, resume emulation. Yeah, it's synchronized. It always remains synchronized. So this took a great bit of time because I'm not so competent, but I'm proud of it. Not the incompetency, but it working. Then I had to implement a method, or I think I need to implement a method, I've not really used this, is to know how far along the track the car is. Because I think the reward for the agent, or part of the reward for the agent, has to be try to make as much progress as possible in a given time, or between steps. So I think if I were to reward it simply go as fast as you can, it might be ignorant about whether it's going through the grass or going the wrong way or doing donuts, and we'll come to this later. So yeah, I wanted to have a track progress, and I couldn't find a variable in the game that does this, so I developed a method. This is that method working, or it's one of the iterations of this method. So here this 99.7 is the track position, so this is saying it's at 99.7 from the finish to the finish line. Cross the finishing line, 0, and again it increments upwards. And yeah, we can jump forward. You can see when it will cross the finish line again, it cuts to 100 and starts again from 0. It's not perfect. I'll explain. So now here's the track progress, and here's the method I used and the issues I have. So I've made a drive recorder, and I've made the computer agent drive around the high-speed ring and record the position of the car at fixed time intervals. And then I have a method that, given the current XY position of the car, calculate the distance from the car to these points and evaluate which is the closest point. And that way you know in which segment you are of the track. It's not perfect because there are a few hurdles. First off, as you saw earlier, this 99.7, I haven't figured out how to deal with it, but Gran Turismo starts at lap 0, so the car is actually behind the start-finish line. I think there's not just Gran Turismo, all real car racing environments are like this. So I don't have a elegant way to solve this yet. The other issue is because my track recorder, flight recorder, records the XY positions at fixed time intervals. How dense or scarce these points are, as plotted here in Excel, vary with how fast the car is driving. So here it's scarce, it slows down for a corner, speeds up, scarce. Here in the very slow part of the section, the dots are closer together. This could be good, could be bad. It's good because, or rather mostly I think it's bad. It could be good if it encourages the driving line. So this XY position actually also embeds how far to the left or to the right of the track. But it's bad because, for example, at the starting line, there are fewer points. So it would mean it would be harder for the agent to learn where the reward is, because it has to take many steps to recognize there's a reward behind these actions that it used to execute those steps. So again, I have a fudge fix. So I basically made the AI agent drive really slow, 80 kilometers an hour. So I forced the engine speed variable in RAM in Redux to remain at a constant. That way it cannot go beyond 80. I don't remember it really was 80, but some slow speed. And to also make the logging at a higher rate, I utilized the high frame rate mode in Gran Turismo. So this is one of the bonuses that's meant to be available for the race, for time trials in night time on one of the night courses. But again, because enough people have developed cheats and I've implemented it in Lua to implement this cheat, I was able to force this high frame rate mode in high speed ring. So basically Gran Turismo is rendering at 25 frames per second, but this mode it's running at 50 frames per second. And you can see how dense it is. This is the same plot at roughly the same size as the previous screen. It looks like a continuous line, but it's not. There are actual dots along here, which you can barely make out. I have some more ideas. So another idea, which I think is, or I now know is similar to what Trackmania did, the guys from Trackmania Reinforcement Learning, which is they interpolate, or establish the gradient equation or the equation to join two dots, and then re-establish dots at fixed intervals. So I think this is cool. I might work on implementing this, but in particular, why I want to do this is for something cooler. So let's assume the car is around this position. I think I can use the closest position and the position before. So sorry, the closest position and the vehicle's actual position to calculate the vector of the car, or the traveling vector of the vehicle. Then I can also calculate the next three ideal vectors according to the track. And what I'm thinking of doing, why I want to think of this, I mean, and 3 is just an example, is with this, if I feed this into the neural network, then the neural network might recognize that it should, its actions should also depend on the shape of the track that's going to come ahead of time, even if it cannot see it. So like around the corner, a blind corner. And you'd think this is cheating, but I was reflecting on this, and a real race car driver kind of memorizes the track. Even if he cannot see the corner, he knows what corner there is. So this is a bizarre twist from, let's say, textbook machine learning, where we normally want to keep models generalized and not overfit and not rely on knowing things that the agent cannot see. In this case, I think it's all fair game, because we're trying to make an agent that can play racing games. And even people who play racing games memorize the track, remember when to brake, when to turn. Even if you cannot see the corner, you're planning how to enter the current corner based on the way the next corner is shaped. So this is definitely something I want to look at in the future. This is the real-time gym that I was talking about, which I've implemented. Again, I'll put a link in the description below. It's really cool, and basically it's about what I described earlier, to cope with elasticity of between the environment and the agent, the machine learning agent. So, and I think this is really useful when you consider it for robotics applications, but I also think of it for real life applications like autonomous driving, or even just for this project, machine learning, reinforcement learning for a video game. So other methods rely on horsepower on the computer side. So I can't remember, but I think Sophie AI, in their paper, they show a whole network of PlayStation 4s or 5s, I can't remember, I think 4s, working together, and computers on the other side. So I think if you have that much horsepower, you can brute force your way to trying to assure you remain in sync. So your prediction or evaluation of what action to take can always be executed fast enough to be in time before the next observation is available. In real life, I think, especially when you have limited costs or resources, this might be on the edge. So you might have an occasional slowdown on your evaluation model, and you might have some slowdown also on your observation methods like digital sensors and so on. And it doesn't necessarily have to be bad design, but you can imagine these things fluctuate with temperature, age, tolerance of production, and so on. So this real-time gym basically handles it for me in the background. It will take a default action when it recognizes that the action it has evaluated is no longer applicable. So if real-time has moved on beyond a permissible factor, it will say, okay, it will assume this action is no longer assured to be reliable within some window of delay, and it will apply default action, which I have not decided yet. For now, I coded it as keep the accelerator on, but don't steer. Random agent. So here is the collation of everything up to here in this video. So the real-time gym environment is implemented, and I'm just grabbing a random action from the action space, so random sample, and executing it and observing the emulator, the car in the emulator do these random actions. So I don't know if you can see that well. The steering wheels are going crazy left to right, and yeah, so I've made it that it cannot turn too aggressively, and it only knows the accelerator. The accelerator is actually being blipped, but yeah, it's cool that finally everything is connected together. So from here, the next challenge was to start the machine learning. But before that, here's a small summary of some of the variables we found, or I found, and Jamie T helped. So tire conditions, I found a variable that seems to indicate relate to which part of the car hits a wall. I think it's going to be useful. I'm going to look into if this could help the agent to learn where is the wall, or perhaps assign a penalty to hitting the wall. I'm not sure. Jamie T helped me find the wrong direction flag, which again I am using and definitely intend to use in order to generate rewards that are only applicable for the forward direction and become penalties when you're going backwards. So then, deploying reinforcement learning. This was a big dilemma. So up till here, we have nothing that has to do with reinforcement learning, and here the tough part begins. So even though I think all of it was tough until here, this is the real thing. So first option is make something custom, or custom while using frameworks and libraries that exist like Torch or TensorFlow, or make your own. Another option is the stable baseline library, and the third option is the Ray and Rllib framework. So these are the pros and cons. So custom, obviously, most flexible, most time consuming, especially with my experience and skill, which also means I might not have enough time to test several algorithms. Baseline tree probably is one of the most common and useful libraries for one of these kind of projects, but it's currently Torch based. So the baseline 2 used to be TensorFlow based only, and now it's Torch based only. So that's again taking away a choice which I have not made yet. And it's Gym based, which is not the latest library. Gymnasium is, and there are some subtle changes which breaks compatibility. Third is this Ray with reinforcement learning library. It has a lot of customization. It's built in such a way that it works with Torch, TensorFlow 1, TensorFlow 2, which means you can exploit the eager mode for evaluation. It's compatible with Gymnasium, so the latest version, and other environments. Cons, it's so powerful, it can be also too customizable. It's actually developed for distributed computing and parallel learning, which is not something I can do because of the way I implemented my environment and the emulator. And it has a very good website, but I find it hard for me to understand. So most of the times you have to look at the source code because there isn't a page that explains what each configuration or tunable feature of the library can do. So yeah, I went with this last option. So far, no regrets. And yeah, we'll see what happened there. So this is cool. So this is a very simplistic version. It's simply the training result from 8 episodes. In this implementation, the agent cannot see the screen. It can only receive the vehicle speed, engine speed, and the gear. It has a simple reward. I'm rewarding it for having a high vehicle speed and penalizing it for having a speed while going backwards. And the actions it can take is accelerate, brake, steer left and right. That's it. As you can see, it doesn't know what it's doing. It accelerates and brakes. And in some video, this is episode 8. Episode 1, it just but it's cool. It's cool that all these Python files and Lua scripts are somehow working together. What does it look like after 400 training loops? It learns that braking is bad. So these are the brake related variables. So this indicates the agent didn't try to apply the brakes, which is cool because before I could see the brakes always flashing. So yes, it's learned braking is bad if you want to go fast. But because it cannot see the world, it cannot easily evaluate if steering is good or bad. I mean, technically steering is probably slowing the vehicle down a little bit, but at these low speeds, it won't be significant enough to impact the reward. And the impact of the steering wheel change comes later because it has to hit the wall. So it will perhaps not recognize that. What else has it learned? It's learned that donuts are cool. So often in these higher episodes, or higher, after like 400, 500 training episodes, it occasionally gets stuck in a spin. So it's understood that mostly keeping the accelerator pedal to the metal is probably good. But once it gets into a spin and it's still going crazy with the steering wheel, the car never stables and it remains in a donut. Which is cool. So, things to still do. Perhaps focus on a simpler track, maybe at least at first, like a straight line drag race, which is available in Gran Turismo. See if it can optimize itself for not slipping the wheels, find the best traction acceleration. Consider which algorithm to use. So, there are many, let's say, non-theoretical explanations out there about which algorithm to use. I want to think about it more academically, theoretically, and perhaps make some hypothesis and comparison. These 3 are actually what I've tested so far, and the 3, let's say, for reasons not explained today, I wish to go with. I've had some issues with SAC, the base vanilla SAC. Yeah, I need to look into that. It could be some of these methods I cannot implement due to the hardware I have available to me. I want to implement the CNN, so the fully visual-based input to the neural network. It's currently big because I have the raw frame size, which is, of course, not too much. It's around, I think, 320 by 240 pixels in full RGB. But I also intend to feed the agent the last 3 frames. So every time it's going to be 4 images, so 4 320 by 240 screens times 3 for RGB. So I want to downsize it and make it grayscale, but before I commit to a size and grayscale, I want to try and play it in that mode. So if I make the screen half size and black and white, or grayscale, sorry, I want to play by looking at the smaller screen in grayscale, because my rule of thumb is going to be, I don't want this agent to be able to do things in conditions humans cannot, but I want to try and make an agent that can do as good or better than humans under conditions that a human would operate. So if it's impossible for a human to understand where's the edge of the track because of grayscale, then I'm going to say, okay, then it's not fair to make the agent do that. I want to consider, of course, in relation to all of this, what else should be in the observable space, or should it detect from the game that it hit the wall? My gut feeling is yes. So in a real car, you'd definitely know you hit the wall. In the video game, you'd know you hit the wall. You also have the sound. So it feels like the agent has an unfair disadvantage that it cannot perceive this. But then on the other hand, tire slip. So we found a variable which shows tire slip in a single bit resolution. So it goes from the value of 0 to 256. We could feed that. We could not feed that. We could downsample it. So for example, I don't know, make it increment in steps of 10, 20, 50. So it has a sense of slip, but not accurately. Or make it digital slip, not slipping. So again, here I'm thinking about it from the human perspective. In a real car, and if you're a good driver, you'll know very accurately how much the tires are slipping, but neither something scientific that you can say, oh, the tires are slipping at 0.632. You'll just feel, oops, we're past the grip, we're on the edge, or, So again, this is why I wanted this project. I wanted to study these what if hypothesis and considerations. And the last thing, if I ever get there, is I'm curious if it learns how, for example, to take corners on one track. And assuming the second track has a similar grip surface, so not like from road to dirt, but road to road, would the same agent start off as capable or similarly capable, or would it start off as being completely idiotic on a new track? So yeah, that's something I want to look into next time. So that's all for today. I hope you enjoyed watching this. It was a pleasure getting this far, and I look forward to the future episodes. Thank you. Take care.